In this video, we're going to talk about functions of several variables. So a function of several variables is much like a function of a single variable. It's just that instead of an input for a function here, instead of being a single number that we're going to plug in, we're going to plug in a whole n tuple of numbers. So like an ordered pair or an ordered triple, we're going to plug a whole ordered n tuple of things into it. So the input is going to be the x1 to xn as a tuple, and then when we plug that into the function, we'll get a real number output. For our purposes, it'll be real number outputs. It could be complex number outputs in other situations, but for our purposes in this class, it will always be a real number output, which we're going to denote using regular old function notation like we've used in the past, just f of x1 out to xn. So, and just like before, for regular functions, we use the same language when we talk about inputs and outputs. The set of all n tuples that we can plug in, that's going to be the domain of f, and the set of all real numbers that we can get out of f will be the range of f. So let's do an example of a specific example here of a function and look at its domain and its range and a couple of outputs. Alright, so let's look at this function of two variables. This function is f of xy equals 3 plus square root of x 25 minus x squared minus y squared. So like I said, let's just plug a couple of values in. So again, when we plug in things here, we're going to plug in a tuple. So we'll plug in a number for x and a number for y. So say we wanted to plug in the point 3 comma 0, we would put 3 in for x, as you see here. We put 0 in for the y, as you see here, and then simplify like you always would. Likewise, if we put in the number 0 and negative 4, we would put 0 in for x and negative 4 in for y, and then again we would see we would get 6 in this case. Alright, let's consider domain. Well, looking at we consider the same type of domain issues for functions of several variables as we do for functions of a single variable. In this case, if you look, we have a square root. Issues with square roots arise when you try to take the square root of a negative number. So for the domain, we're going to need to make sure that what's underneath the radical is greater than or equal to 0. So if we simplify this, or at least rearrange the inequality, we get the x squared plus y squared is less than or equal to 25. If this was equal to 25, we would recognize this as the equation of a circle. So this example what we have is that here we have a circle and its interior, or the set of all points that satisfy that inequality, will be the domain of f. A lot of times, to illustrate what's going on, we will graph the domain of the function. So in this case, the graph would just be the circle of radius 5 and its interior. I should say the circle of radius 5 centered at the origin and its interior. So this disk, if you will. How about the range? Well, we know that the absolute smallest that x squared plus y squared can get is 0, meaning we can't subtract. So notice this is 25 minus x squared plus y squared, right? So the x squared plus y squared always has to be at least 0. It can't get any smaller, meaning that the biggest the underneath can get is 25. Or when you take the square root, the biggest it can get is 5. And then again, we're also doing the square root of this thing. The smallest the square root could ever get is 0. So this piece right here, the square root of 25 minus x squared minus y squared, that piece right there has to be between 0 and 5, and we're adding 3 to it. So the range has to be all of the numbers z, and usually we associate the variable z as the outputs. All the variables, all the numbers z such that 3 is less than or equal to z is less than or equal to 8. Alright, so now let's talk about how we would sketch a graph of a function of several variables, and we'll do a couple of straightforward examples. So let's say we just had the sketch of f of xy equals x squared. Alright, so notice this kind of reminds us of when we have a graph of a horizontal line or a graph of a vertical line where the variable is missing. In this case, the y value is missing. So that tells us y can be absolutely anything when we graph this. Okay, just keep that in mind. So the first thing we're going to do is we're going to graph the equation z equals x squared in the xz plane. So let's talk about that for a second. So here is a three-dimensional picture, three-dimensional axes, if you will. So here's the x-axis, here's the y-axis, here's the z-axis. So this is three-dimensional space, or Cartesian 3 space is another word for it. Anyway, so we've got different planes here. So this x value, this x is representing, of course, the x-axis is red. The green one's representing the y. The blue one's representing the z. When we talk about in the xz plane, we're treating y equals 0, and we're looking at this plane that's determined by the x-axis and the z-axis. So this parabola here, z equals x squared, is in a plane where y is equal to 0. Okay? Notice it looks, I don't know, smashed, if you will, because again we have to do perspective. We're trying to put a three-dimensional picture on a two-dimensional piece of paper or a two-dimensional screen, as the case may be. So we've got to draw with perspective, if you will. So this really what would be happening is that this y-axis would be kind of running in the screen left right. The z-axis would be going up and down in the screen. The x-axis then would be coming right out of the screen at you. Okay, so we have to turn it a little bit, so that's perspective. So this piece here for the z equals x squared would be coming out of the screen, and this would be going behind the screen. All right, again, y can be absolutely anything, so we can extend the graph of this z equals x squared infinitely in both y directions, much like what we do for a horizontal or vertical line. So we take this z equals x squared graph and we extend it back in the negative y's or out in the positive y's, and we get this bent shape, if you will. When we graph a function of two variables, we get what's referred to as a surface. We plug in an x, y, we get a z, we get a surface when we graph it. This particular type of surface is referred to as a cylinder, and cylinders occur when you get the same congruent shape extended indefinitely in one of the directions. So we just refer to that as in general, we refer to it as a cylinder. All right, let's sketch another one. Let's sketch the graph f of xy equals 9 minus 9x squared minus y squared. We're going to, much like what we did in the previous example where we looked at the z equals x squared and graphed it, we're going to do what we refer to as traces, and not just do the xz trace. That's what we did last time, was what we referred to as the xz trace. But let's do the other traces with the other coordinate axes. The xy plane, this should say each of the other coordinate planes, not axes, so this is the wrong word. This should be coordinate planes here. It's the intersection with those planes. So let's look at the xy trace. The xy trace would mean that the z is equal to 0, because that's if you're intersecting with the xy plane, you haven't gone up or down at all. So we would have 9 minus 9x squared minus y squared equals 0. Put that in standard form, we get an ellipse. Remember, the denominator tells you, for each of them, tells you how far front and back you would go in the x direction, left or right you would go in the y direction. So this would go out and back 1 in the x direction, and then out and back 3 in the y direction, and it's centered at 0, 0 because we're not subtracting anything off the x or the y. Xz trace, we put in 0 for y, so this term would go away. I guess up here a better idea. This term would go away. We would have z equals 9 minus 9x squared. That's a parabola. Likewise, if we do the yz trace and put in x equal to 0, we get z equals 9 minus y squared. We also get a parabola. Alright, so we graph those traces. Here's the ellipse in the xy plane. Here's the parabola in the xz plane. And here's the parabola in the xy plane. Notice that the parabola in the xz plane is steeper, right? Because it's got that 9 on the x squared. So steeper for the x direction than the y direction as far as the parabola goes. These are downward facing parabolas and they cross the z-axis at 9. That's how I knew to draw them this way. And now we get a pretty good idea of what's going on with this graph. Right? So here is our trace, here's our trace, here's our trace. We see those three traces. And we get this particular type of shape, which is called an elliptic paraboloid. You can probably see pretty quickly where those words come from, the elliptic and the paraboloid, just by the traces that we got. Another way to investigate graphs of surfaces is looking at level curves. So in the previous one, let me just scroll back to that real quick. Notice that if we slice with planes that are parallel to the xy plane, or said another way, set z equal to a number, those was what gives you the level curves, those slices. If you've ever seen a topographic map, that's the idea. It's all of the points on the surface that have the exact same height, or the exact same z value. So a topographic map, all the lines on a topographic map connect all the points that are at the same altitude. Okay. So in this case, if we put in a number for z, we see we get ellipses like we did here. So if we just change out some numbers for z, doesn't really matter what they are, but I picked those 7. Here's what your level curves would look like. At z equal to 9, you're at the top, and then you get these widening ellipses as the z gets lower and lower, which again, if I go back to the original graph, here's z equal to 9, hits that at a point, that would be tangent to the surface, and then the farther down you go, the bigger the ellipses get. And notice that they get tighter together because the z value changes more quickly with respect to x and y, if you will, the farther you go down. It gets steeper. That's what these level curves are telling you as you get farther away from the origin here, is that the graph is getting steeper, which again, if I go back to the graph, you can see that, right? It's bent downward. Let's look at one more. Let's just sketch some level curves for this. Again, when you're sketching level curves, you're just picking some values for the z and then graphing the associated xy curve, whatever that relation happens to be. So we picked a few and rearranged the equations, and we see 3 sine curves, right? -2 sine x, 3 sine x. We see 3 sine curves. So then the corresponding level curves would look like this, right? Here's your 3 sine x is the green one, the blue one is the sine x, and the red one is the -2 sine x. Technically, where this is crossing the x-axis here, we wouldn't have those points included for level curves, because if we go back up to the original function, cosecant x is not defined at that x equals 0 or pi or 2 pi, so technically there should be little holes there. But again, we're not really worried about what it looks like, because we're just trying to use the level surface, the level curves, to try to get an idea of what the surface looks like.